Welcome to the last topic of the semester. This is a big topic. This notion of isomorphism is a really, really big idea, and it's important. And it's going to take us, honestly, 4 or 5 lectures to get through this. We have to understand this, and this might be a little bit hard to do remotely, but we're going to try. I'm going to try to baby step this for you. So let's talk about this notion of isomorphism and what it means. So, in a nutshell, two groups might be technically different. They aren't the same, but they actually might have exactly the same algebraic and group structure. All right, they might be absolutely algebraically identical, but they're technically different. So the things that would make them technically different are just negligible. They don't matter. They're unimportant. And so we want to be able to ignore the differences that don't matter. That's the whole point of this. Ignore the differences that don't matter. We want instead to be able to focus on the essential algebraic anatomy of a group, okay, and not the little details that don't have anything to do with anything else, okay? And when two groups have exactly the same algebraic structure, they're called isomorphic, okay? And this is an essential idea in all of, certainly, abstract algebra, but it's also a big deal in mathematics. You see this in other branches of mathematics, possibly under a different name. Okay. So let's try to get used to this. This might sound strange, but with enough experience, it becomes second nature. And the way to understand this, I think, is to first spend some time with an example. So let's do an example together, okay? Suppose we have a group G, and the group G is made up of 4 elements, E, A, B, and C. The operation on G is called star, and here's the table. Here's the Cayley table that outlines the group operation. And at the same time, suppose I had another group L. And L is made up of the symbols 1 and pi and W and heart. And the operation on L is called diamond. And here is the Cayley table that describes the operation on L. And you can check if you want that both of these really do define the table for a group. All right, so these are actual groups. So before we get any further, let's agree that these two groups are different. All right, they are legally not equal. They are unequal, they are different, they are not the same group. And here are 3 reasons why. Right? The 3 reasons why are, first of all, the groups have different names. One of them I call G, and one of them I called L. So they have different names. Right? The second thing, this is much more substantial. The sets making up the groups are different. In other words, the elements in each group are different from the other one, right? So in one hand, my elements are E and A and B and C. And on the other hand, my elements are 1 and pi and W and heart. And those are different sets, right? These are different sets of objects, and so the groups are different. And the third reason the groups are different is because their binary operations have different names. One was called star and one was called diamond. So these things are unequal, they are different, they are not the same, okay? However, I claim that all these differences are superficial and they don't have any real impact on their algebraic structure. In fact, this might not be obvious yet, these groups actually are algebraically the same. All right? In modern language, we would say these groups are isomorphic to each other. These groups are algebraically the same, and we want to spend some time understanding that, even though they're different. They might not look algebraically the same. There's some things that do look sort of same. They are algebraically made up of 4 things each. Okay, well, that's something. Looks like they both have, let's see, this has 2 occurrences of the identity on the diagonal. This also has 2 occurrences of the identity on the diagonal. This has 2 B's on the diagonal. This has 2 pi's on the diagonal. That seems common. They both have one diagonal this way made up of all the same elements. This is 4 hearts this way, and this is, 4 C's this way. That seems the same. But they don't seem the same because here you have 3 B's and 3 E's, and here you don't. You have W1W and W pi W. So they don't look the same algebraically, but it turns out they are. So let's look more deeply at this. What does it mean to say they're algebraically identical? So let's look at G first. G has some properties. You should look at the table of G and notice that G is abelian. G is cyclic. It has 2 generators. The generators are A and C. And the 2 generators that it has are actually inverse to each other, all right? So A generates G and C generates also G as well, and A and C are inverse to each other. G has a unique element of order 2, namely B. Right? If you look at the table for G, B squared is the identity, and no other element besides the identity, which is order 1, has that property, so it has a unique element of order 2. G also has only 3 subgroups. It has the trivial one, the subgroup that contains E and the element of order 2, and the whole thing itself, the improper subgroup. And these are all algebraic properties of G. And let's look at the properties of L. Well, if you look at the properties of L, L has the exact same list of properties. G was abelian. Guess what? L is abelian. L is cyclic and it has 2 distinct generators, W and heart. That should sound familiar. And the two inverses, the two elements that generate, W and heart, are inverse to each other. That should sound familiar. L has a unique element of order 2, namely pi. If you look at the table for L, pi squared is the identity. Nobody else is the identity except for the identity, which is order 1, not 2. Right? So L has a unique element of order 2, and L has only 3 subgroups. The trivial subgroup should sound familiar. The subgroup containing 1 and the element of order 2 should sound familiar, and the improper subgroup. So this is the exact same list of structural properties of G, just with different names. Instead of there being a unique element of order 2 called B, there's now a unique element of order 2 called pi. Well, who cares about the name? The name doesn't matter. Okay? So G and L are algebraically identical, even though they're different. And in group theory, we don't care that they're different. Right? What we care about is their algebra. And as far as the algebra goes, they're not different. They have the same algebra. So we'll say they are isomorphic. This is the idea of isomorphism. Okay? So we would say that G is isomorphic to L, meaning that the two groups are structurally identical. But we got to make sense of this. I can't just say that in words and do math. I need to make it rigorous. So to make mathematical sense of this, we're going to learn how to compare these two groups using the best comparison tool that's ever been invented, functions. That is what functions are for, comparing two things. So we somehow need to give a transformation that will take the group G and morph it into the group L in a faithful way. So I'm going to do that by a function. Now what I'm going to do is I'm going to give you a function that takes the Cayley table for G and it's going to morph it into the Cayley table for the group L. Okay? In order to do that, I first need to rearrange L a little bit to make it look more like G. Remember, here's what G looked like. Right? It had these B's on this subdiagonal and these trio of E's on the subdiagonal that L didn't have. Well, that's because L wasn't written in the best possible way. If I take the Cayley table for L and I switch the middle two, before I wrote it as 1, then pi, then W, then heart. Now I'm going to write it as 1 W pi heart. If I write the table with a different header row and a different column header, and then I just do the same multiplications, look, the tables now look identity. Pi, 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 B, 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 1, 1, 1, E, E, E. And I didn't alter the operation of L. It's the same operation. It's just the table gets rewritten, right? In both versions of the table, both before and after I reordered them, I still had pi operate heart is W, right? Here, pi operate heart is W when I reordered it. In my original table for L, pi operate heart was still W. I didn't change any of the operation. I just changed how it was displayed in the table. But now you can see that I can actually generate this table from this table if I take every E that I see and make it a 1. Take every A that I see and make it a W. Take every B that I see, make it a pi. Take every C that I see and make it a heart. So make every E a 1, every A a W, every B a pi, every C a heart. That will take this table and generate this table. But this is a function, right? This is a function that has domain EABC and has outputs 1 W pi heart. So this relabeling is a function. I can define a function alpha that goes from G to L by that exact same relabeling scheme. Alpha E is 1, alpha A is W, alpha B is pi, alpha C is heart. And alpha will create the table for L out of the table of G. This function alpha that goes from the group G to the group L in a faithful way, and it takes the group G and it actually creates the group L, is called an isomorphism. And when an isomorphism like this exists, you say that G and L are isomorphic. That's the idea. This relabeling scheme here is a function, and that function tells you how to manufacture this group out of this group in a faithful way. So in the next handout, we're going to make this rigorous and actually give the rigorous definition of an isomorphism, and we'll start to look at the structure and the properties that isomorphisms have and why you would do this.